So when Rutherford's experiment was happening, so it was observed that whole of the atom's mass was concentrated in the center, and the center consisted of positive charges. So at that point of time, during the time of Rutherford's experiment, when he coined the term nucleus, what did people think? The nucleus was completely of positive charge. But today we know that nucleus consists of positive charges and the neutral particles called as the neutrons. Means at that point of time, neutrons were actually not invented. Okay. Later, it was invented by a scientist named James Chadwick. So James Chadwick was a scientist who found that neutrons also existed within the nucleus, and that was also found based on some radioactivity experiment only. Okay. So anyways, we are not going to get into details of how this experiment happened. That is none of our business. So in this chapter, we are going to concentrate on different terms that are there in the nucleus and what do we need to understand about them. Okay. So let's see the topics that are covered in this chapter. First is we need to understand the introduction of nuclei. Second is we need to understand the atomic masses and composition of nucleus. Third, we need to speak about the size of the nucleus. Then we have a relation called as mass energy relation, which we have already seen, which is E is equal to mc square, proposed by Einstein, which is energy mass equivalence relation. And there is something called as nuclear binding energy. Then we have nuclear force. This radioactivity and nuclear energy are not there, so we need not worry about them. Okay. So as the first topic is introduction to nucleus, as I already mentioned, the atomic nucleus was discovered by Ernest Rutherford in 1911. This we have already discussed. So Rutherford's experiment on scattering of alpha particles proved that mass of the atom and the positive charge is concentrated in a very small central core called as the nucleus. Okay. So the dimension of nucleus on a comparative scale with the size of the atom. So the dimension of a nucleus is much smaller than the overall dimension of the atom. So the nucleus is surrounded by orbiting electrons. Right. So this was the discovery. But today we know that nucleus consists of what? The elementary particles, protons and neutrons, which are collectively called as nucleons. I told you, right? There is a topic that is deleted, which is called as binding energy per nucleon. Nucleon means the neutrons and protons put together. Okay. Now the question comes, what is a proton? So proton has a positive charge and its magnitude, the magnitude of the charge of the proton is same as that of the electron, and its rest mass, there is something called as rest mass, which is about 1836 times the mass of an electron. Okay, that is when the particle is at rest, its mass is going to be 1836 times the mass of an electron. Then what about a neutron? A neutron is electrically neutral, whose mass is almost equal to that of the proton. So when you try to measure in terms of kilograms, you can observe that both of them will have same amount of mass. But we'll be seeing another unit which you people already know, which is called as AMU, atomic mass unit. When you see them in atomic mass unit, they will be, you can see a slight difference in them. That is why it is mentioned that it is almost equal to the mass of the proton. Third, the nucleons inside the nucleus, how are the nucleons held inside? That's the question. So if you talk about the electron and the nucleus, how are the electrons bound to the nucleus? What is the force that is holding them?
Centripetal force.
Centripetal force. And that centripetal force is provided by which force? See,
Electrostatic
centripetal,
force.
it is the electrostatic attraction that is existing. Right? In a similar context, if you talk about the way protons and neutrons are bound together, that is happening because of a force called as nuclear force, which is very much stronger. Right? So remember this word, nuclear forces. By strong attractive forces called as nuclear forces. So a nucleus of an element is generally represented by XAZ, where X is the chemical symbol of the element, and Z represents what? Z represents the atomic number. So atomic number is a technical name, but in terms of number, what does that atomic number actually signify? It signifies the number of protons, and A stands for the mass number. So the mass number signifies what? Which is equal to the total number of protons and neutrons, which is collectively called as nucleons. Okay. Then what about the number of neutrons? The number of neutrons are represented by A minus Z, because we know that A is equal to Z plus capital N, which implies N is equal to A minus Z, where N represents neutrons A represents the number of nucleons and Z represents the number of protons. If anybody is having a confusion about it, please make a note of it. I'm sure you would have been strong by now. So if you take the example of chlorine nucleus, which is represented by Cl35 and 17, then it contains 17 protons because its atomic number is 17 and 18 neutrons. We got that 18 because of 35 minus 17. And it contains 35 nucleons. Right? I hope it is clear till this step. It's an easy concept, right? Is there any doubt?
No.
Okay. I'll proceed then. So we will see what are the classification of nucleus. See, wherever you see classification, classification should have some differentiating factor. On the basis of what is nuclei classified as three types, which are named as isotopes, isobars, and isotones. What is the differentiating factor? This also you know. So what do you mean by isotopes? So iso means same. Okay. So here isotopes are the atoms of same element having same atomic number but different mass number. For example, when you talk about the isotopes of hydrogen, we have H11, H21, and H31. These are the isotopes of hydrogen. In other words, what can you say? Isotopes are those elements. Okay. Sorry, isotopes of elements are the ones which have the same number of protons but different number of neutrons. You can state it like this. Similarly, as the atoms of isotopes have similar electronic structure, they have identical chemical properties and they are placed in the same location in the periodic table. This about isotope. Then what is an isobar? So isobars are atoms of different elements. Isotopes are of same element. Isobars are of different elements having the same mass number, means they have the same number of nucleons, right? But different atomic number. So if you take oxygen, so O16 and 8 and N16 and 7 represent two isobars because they say have the same mass number. Okay. Since our isobars belong to are atoms of different elements, they have different physical and chemical properties, whereas isobars have the same physical and chemical properties. Next is isotones. So what are isotones? Isotones are atoms of different elements having the same number of neutrons. So neutrons is A minus Z, N is equal to A minus Z. So if you take carbon 14 and oxygen 16, then 14 minus 6 is going to give us 8 and 16 minus 8 is also going to give us 8, and they are called as isotones. Right? So this is also a familiar concept to you guys. Shall I proceed?
Yes, sir.
So this is an important concept. So what are the general properties of nucleus? Okay, what are all the different, I can say, what are all the basic terminologies that are associated with nucleus? There are six general properties, out of which the first thing that we are going to look into is called as nuclear size. Then we will discuss about a concept called as nuclear density. Then comes nuclear charge. Then comes atomic mass unit. Then comes nuclear mass. And lastly comes binding energy and binding energy per nucleon. Okay, so concentrate. So when you talk about the general properties of nucleus, okay, so the first is nuclear size. So nuclear size was already described in the case of Rutherford's experiment. So according to Rutherford's alpha ray scattering experiment, remember he proposed that at the nucleus is approximately of the size of 10 power minus 14 meter, right? So according to the Rutherford's alpha particle scattering experiment, the distance of closest approach of alpha particle to the nucleus was taken as a measure of radius of the nuclear radius, which was approximately 10 power minus 15. Okay. So 10 power minus 15 meter is generally called as 1 Fermi. Okay. So if the nucleus is assumed to be spherical, as I told you, nobody has seen what it is. Okay. So if the nucleus is assumed to be spherical, and empirical relation. So empirical is so there are two types of statements that we do. One is empirical and the second is statistical. That is, we do an analysis and do it. Empirical relation is something based on observation, we come up with a theory. So an empirical relation that is found to hold good between the radius of the nucleus r and its mass number is given like this. The radius of a nucleus is observed to be directly proportional to the cube root of its mass number. This is an important relation. Please make a note of it. Questions will be asked based on this. You can get 1 mark questions, which are problems which are based on this concept. So the radius of a nucleus is directly proportional to what? Cube root of the mass number. If you remove the proportionality symbol, the constant that we introduce is r naught into a power 1 by 3. Okay, where this r naught is going to be 1.3 Fermi. Where 1 Fermi is what? 10 power minus 15 meter. Don't get confused between this and farad. Farad is used in the concept of capacitors. Here we are talking about the nuclear size. So that is the first general property of a nucleus. I hope it is clear. Right? So I want you all to please make a note of it. Done?
Yes, sir.
Okay. So next comes the concept of nuclear density. So as we know, density, here when we speak about density, we are not trying to speak about its charge density. We are trying to speak about its mass density. Okay. So nuclear density can be calculated from the mass and the size of the nucleus. So size of the nucleus is given by the previous topic. So if I have to define its mass density, okay, let's think logically. If I have to define its mass density, then rho n is given as mass of the nucleus, that is called as nuclear mass, divided by what? Nuclear volume, that is the volume of the nucleus. So what is the nuclear mass? Who's responsible for the mass of the nucleus? Let's think about it. So inside the nucleus, what are all the particles that are present?
Neutrons.
Protons and
Neutrons and
neutrons.
protons.
Right. So each proton, let's say the proton's mass that is associated is mp, and let's say mass of the neutron is mn. Okay, I'm writing capital N. Then how many neutrons are there and how many protons are there? So can I write it as z times mass of each proton, because you have z number of protons, and how many neutrons are there? Can I write it as a minus z into mass of neutron, the whole divided by nuclear volume. When I speak about its volume, I need to know its shape. So its shape is assumed to be spherical. So for a sphere, what is the volume? It is 4 by 3 pi into r cube. Am I clear, guys? So look at the one that I'm writing. Okay, don't concentrate on the left hand side. Now comes the important point. As we told that NP, mass of the proton, is approximately equal to the mass of the neutron, can I write rho n is equal to z times mp plus a minus z times mp, the whole divided by 4 by 3 pi into, in the place of r, can I write it as r naught into a power 1 by 3, 4 pi r naught cube into a, because a power 1 by 3, the whole cube is a. Right? So what will happen is z times mp and z will get cancelled. So you will have 3 by 4 pi r naught into a divided by a times mp. This and this will get cancelled. So you will have 3 times mass of proton divided by 4 pi r naught cube. So this is the density of nucleus. So an important point to be noted from here is 3 times mass of proton. So 3 and mass of proton both are constant, divided by 4 pi is a constant and r naught is also constant, which is 1.3 Fermi. So from that, can I conclude that the nuclear density is always a constant? Right? So an important conclusion to be drawn from here is the nuclear density is constant for all the nuclei irrespective of its size. And when you substitute all the values and calculate, it comes out as 1.816 into 10 power 17 kilogram per meter cube. Means if you take a 1 meter cube volume, in that how much mass is present? 1.816 into 10 power 16, 10 power 17 kilogram. Try to understand the mass of the protons is how much? Mass of the proton is approximately 10 power minus 27. So if that mass has to come to 10 power 17, imagine the number of protons that have to be put within a 1 meter cube volume. Means more number of particles are cramped within a smaller volume. So from this, which we can say that its nuclear density is very high and the nuclear matter is in extremely rich state. It's in a very much compressed state. Are you able to understand? So nuclear stability is a very, very important thing, or else a nuclear reaction is possible, which is with the disintegration is what is called as radioactivity. Look at the state in which it is. It is in that much compressed state. Am I clear, guys? An important point. I hope you made a note of it. Right? So proceeding to the next concept. The next concept is nuclear charge. Now comes the question again. Inside the nucleus, who is responsible for the charge of it? It is only protons, because neutrons are going to be a neutral particles, right? So charge of the nucleus is due to the protons present in it. So each proton has a positive charge of how much value? 1.6 into 10 power minus 19 coulomb. So from this we can conclude that the nuclear charge is Zt. You remember in the last chapter I used Zt for the derivation process. Here Zt and the electrons will revolve here which have charge E. So to calculate the radius between them, we used K into Zt into E divided by R square. The reason for Zt is because of the concept of nuclear charge. So as we know, Z number of protons are there. Z multiplied with charge of each proton will give us the total charge of the nucleus. That's called as nuclear charge. There is no specific symbol for it. You can just remember it as Zt. Okay. Next comes the important topic, that is atomic mass unit, which we also call it as AMU. This also you people know what it is. Right? So how is it defined as? It is defined as the mass of 1 by 12 of a C12 atom or a carbon 12 atom. So one atomic mass unit is considered as the 1/12 of the mass of carbon atom, which is C12. Okay, C12 is the main atom. So 1 by 12th of its mass is considered as one atomic mass unit. By substituting all the values and calculating, one atomic mass unit is equal to 1.6 into 10 power minus 27 kilogram. Okay. So as I told you, instead of writing mass of proton and mass of neutron in terms of kilogram, if you write it in terms of AMU, then the mass of proton comes out as 1.007276 AMU, and the mass of neutron comes out as 1.008665 AMU, which is slightly of a greater mass. Neutron is of a slightly greater mass, but on a comparative scale, they both are almost equal because AMU is a factor of 10 power minus 27 kilogram. Okay. So also we discussed one more important point in dual nature, that the energy in this chapter, energy in the case of atomic physics and nuclear physics is measured in electron volt. So you remember I told you there is an energy mass equivalence relation which is called as E is equal to mc square. Right. So the energy equivalence of one AMU can be calculated in terms of electron volt. How are we going to calculate it? So the question is like this. What is the energy equivalent of one AMU? Means one AMU consists of how much energy in terms of electron volt. So how to calculate this? Observe. So E is equal to, when I say mc square, one AMU is how many kilograms squares? It is 1.66 into 10 power minus 27 kilogram. C square is how much? It is 9 into 10 power 16 meter square per second square, accepted. So what will I get when you multiply kilogram meter square per second square? Kilogram meter square per second square is called as joules. Right. So you guys can use calculator. Tell me what is 1.66 into 9. I think this is a simpler one. 1.66 into 9 is how much? into 10 power minus 27 into 10 power 16 is 10 power minus 11 joule. So 1.66 is 5459. How much is this?
14.
14 point,
14.
14.
14.94 into 10 power minus 11 joule. But what are they expecting? They want 1 AMU's equivalent energy in terms of electron volt. That's what we are going to use in this chapter. We know that 1 joule is how many electron volt? 1 joule is 1 divided by 1.6 into 10 power minus 19 electron volt. So what you can do is use your calculator. Calculate what is 14.94 divided by 1.6 into 10 power minus 19 and tell me. I mean, you multiply with 10 power minus 11 also. So what is 14.94? How much?
9.337 into 10 power 8.
9.337 into 10 power 8, right? So can I write this as 933.7 into 10 power 6 electron volt? Right? So this 10 power 6 is nothing but 1 million. 1 million is 10 lakhs. Right? So it is 933.7. This 10 power 6 electron volt, can I write it as MeV, where capital M represents mega or million. So 933.7 million electron volt or mega electron volt means 1 AMU of a nuclei has an energy equivalent of 933.7 mega electron volt. So going forward, wherever you see 1 AMU, you can exactly replace it with 933.7 mega electron volt. Okay. But in books, what they give is 931 mega electron volt. Or some books give it as 931.5 also. Both of them. But I just wanted you to know why that number has actually come. So please make a note of this point. Is there anything that is not clear? So assuming it is clear, I'm proceeding to the next concept. The next general property of nucleus that we are going to see is nuclear mass. So as the nucleus contains protons and neutrons, the mass of the nucleus is assumed to be its constituent. So how do we calculate its assumed nuclear mass? So it is Z times Np because Z stands for the mass of each proton plus N times Mn. N is what? The number of neutrons. So capital N times mass of neutron, right? Can I write it like this? Where Mp and Mn are the masses of the proton and neutron respectively. Okay. So this is not called as nuclear mass, rather what is the term that we have added before it? It's called as assumed nuclear mass. The reason why it is called as assumed nuclear mass is, in reality, this is what we expected. But what happens is, when you try to measure the mass by using mass spectrometers, so those are the devices which are used for measuring the mass. So when you take a stable nucleus means the one which does not get disintegrated. Okay. Stable nucleus comes from a stable atom. It's found that the mass of a stable nucleus is less than the total mass of the nucleons. So this is called as total mass of nucleons. Also, we can call it as assumed nuclear mass because this is a theoretical value which is expected by us, but in reality, when you use a device and measure, the value, let's say it is coming out as X. Okay, if it is coming out as X AMU, when in reality, what will happen is when you use mass spectrometers, it will be a value definitely less than X AMU. Okay. So that's the point. There's a very, very important point. Concentrate. However, from the measurement of mass by mass spectrometers, it is found that the mass of a stable nucleus M is less than the total mass of the nucleons. So, assumed mass of the nucleus is definitely less than Z times Np plus M times Mn. The reason for it we will see. Okay. So, if I call the actual mass as M, observe. If I call the actual mass as M, then what is assumed mass? Z times Mp plus N times Mn, right? Then the Z times Mp plus N times Mn, which is the assumed mass minus the actual mass, is what is called as delta M, because you're finding the difference, and this delta M is called as mass defect. Okay, so this delta M is what we call it as the mass defect. So how do you define mass defect? It is the difference in the total mass of the nucleons and the actual mass of the nucleus. Why it is happening, we will see. Am I clear till this point? Guys,
So what is NMN, sir?
capital N. No? Capital N is the number of neutrons. See, what does a nucleus consist of? It consists of protons and neutrons. So if I take Mp as mass of protons, how many protons are there? Z number of protons. Plus, if I take mass of each neutron as Mn, how many neutrons are there? Capital.
Okay, sir.
I hope this. Yeah. See, there is another way to write also. Can someone tell me how do you write the same thing in terms of mass of a nucleon? You can write it as Z times Mp, or I can write it as A minus Z into Mn. Both are right. Because capital N is nothing but A minus Z. This is another way. If at all you see this kind of a description in some book, don't get confused. Right? Shall I proceed?
Yes, sir.
Yeah.
Yes.
Now comes the important question. Why is this actually happening? If there is a decrease in mass, then according to the energy mass equivalence, what should have happened is there should have been an equivalent amount of energy that is spent in this kind of a defect to occur, and that energy is called as binding energy. So now we are going to connect the dots. When we read about nucleus, when we saw the introduction of nucleus, I told you one important point. A nucleus is an element where, the nucleons inside the nucleus are held together by strong attractive forces called as the nuclear forces. Now comes the question. See, let us assume before let's forget about nucleus and all. I have an empty bag. Okay. So I'm trying to make this empty bag similar to that of I'm trying to exactly replicate the model of a nucleus on a real-time experiment. Okay. If I put a positive charge here, okay, I need another proton. This positive charge is similar to a proton. So I have already put a positive charge in this bag. I'm trying to put another positive charge in this. Will this naturally happen, or do I need to do some work?
Work is needed.
So can you repeat? I didn't hear you.
Work is needed.
So work is needed. What work we need? We need to do a work against something. What is that something?
Repulsive force of it.
So there is a repulsive force existing between the similar kind of particles that you're trying to put. Okay, let's say there is a neutron which is sandwiched in between. But still you can see that there is a kind of, there is going to be a repulsive force. So imagine, you remember the nuclear density. So nuclear density is so high that all these protons are brought and clubbed together. Imagine the amount of work that we need to do. Okay. And what is the purpose of we doing all these works? Because we are trying to replicate the structure of a nucleus. So in the nucleus, all the protons are within them. They are not getting disintegrated. The nucleus is not breaking. Disintegrated means it's breaking into pieces. It's not happening due to the repulsive forces, right? It is still be able to be stable. So if it has to be stable, it has to release some energy, right? So that energy which is released is what is generated in the form of mass defect, because energy and mass are equivalent of each other. Energy and mass can be always interrelated. Okay. Now let me read this out. Then you will understand this one. When the protons and neutrons combine to form a nucleus, the mass that disappears, that is the mass that is lost, is converted into what? Is converted into an equivalent amount of energy, which is called as delta mc square. I told you, right? Energy and mass are equivalent, right? So which is called as delta mc square. This energy is called as the binding energy of the nucleus. Okay. So how do you define this binding energy as? So binding energy is given as, when I say delta mc square, delta m can also be written as z times mass of proton plus n times mass of neutrons. I actually, you can use capital N, okay, for neutrons, minus small n into c square. Okay, z times mt plus n times mn minus the actual mass times c square. So this is going to be the formula for binding energy. Okay, and this is the most important factor or the general property of a nucleus, because this particular parameter, okay, this particular parameter called as binding energy, will decide which nucleus is stable and which nucleus is unstable. See, though they have cancelled radioactivity, right, though they have deleted, I'll give you a slight introduction so that you'll understand why you're studying all these things. Actually, all these things you are learning is related to the stability of a nucleus. Okay, so here there comes the important point. The binding energy of nucleus determines its stability against disintegration. Means whether the nucleus is going to stay intact or it will get broken into pieces. Okay, that's what is meant by disintegration. In other words, you can also conclude, if the binding energy is large, then the nucleus is said to be stable and vice versa. Because the binding energy is more amount of energy is released in the process of binding. Binding means bringing them together. Okay, more energy is released. So since energy is released, it will try to keep itself stable. Because try to understand, in this world, whichever has more amount of energy will not be stable. Okay. So the extended concept of this binding energy is, if you know how to calculate binding energy, let's say binding energy comes out as Be. If the found value of binding energy is divided by the mass number, then this has a technical name called as the binding energy per nucleon. Okay. So binding energy per nucleon. Nucleon is nothing but the number of protons and neutrons put together, which is going to give us the total number of nucleons, which is mass number. Okay. That's just a term. So when you calculate this value, it is found that the binding energy per nucleon varies from element to element. So based on this, what we can do is a graph is plotted with the mass number A of the nucleus along the x-axis and binding energy per nucleon along the y-axis. So that's what is removed actually, and its variation with mass number. But I suggest you to understand this so that you will have clarity when questions are asked. So I'll show you the graph. So this is the binding energy per nucleon measured in megaelectron volt versus mass number taken on the x-axis. If you see that, you are able to see this graph, right? So it's starting from here. The graph is moving like this, then it is going up, coming down. So this is the graph. So for different mass numbers that are given in the x-axis, the binding energy is found in, binding energy per nucleon is found in terms of megaelectron volt, and this kind of a graph is plotted. Okay. For you to understand, see, this graph has not come out randomly. Everything is calculated, pre-calculated values. They've just given the final output to you. But in order to understand how those values are calculated, I will just give you one sample problem. We will try this. So you can write down this question. calculate the binding energy per nucleon of calcium 40 and 20 nucleus, calcium 40, 20. So the mass of calcium is found to be 39.962589 AMU. Mass of neutron is 1.008665 AMU, and the mass of proton is 1.007825 AMU. So for this problem, I'm okay for you using the calculator. So you can use a calculator for calculations, but understand the concept. If there is any doubt, ask. Okay. So what are they asking? They're asking us to calculate the binding energy per nucleon. So what is the binding energy formula? It is delta mc square, right? So first, let's find out what is delta m. What does delta m represent? Z times mass of proton plus A minus Z times mass of neutron, right? So delta m will be equal to, what is the value of Z, guys? 20 into mass of each proton is given as 1.007825. Remember, everything is in AMU. Plus, 1 minute, minus actual mass. A minus Z is how much? That is also 20 into mass of each neutron is 1.008665. This is also in AMU, minus, what is the actual mass of it? It is 39.962589. Right. So can you guys calculate this and tell me fast?
Zero point three six
How much? 0.37
to 81.
to 81. No?
Yes.
So this is the mass defect that we have found. Okay. So how do we find binding energy? You know delta m 0.367281 into c square is how much? 9 into 10 power 16. Am I right? Yes or no? So are you able to
Yes,
understand
sir.
why 9 into 10 power 16 came actually, right?
Hmm.
But this is wrong, because you need to multiply it with 9 into 10 power 16 am 9 into 16, 10 power 16 only when you have measured the mass in kilograms. Okay, here you have measured the mass in what parameter? You have already measured it in, okay, I will write that wrong step so that when you refer it, you will understand. Yes. Into 9 into 10 power 16, this is wrong. Don't do this mistake. So what are we supposed to do? 0.367821, and we know that 1 AMU is equivalent to 1 AMU is equivalent to 931.5 mega electron volt. So what you simply need to do is, if everything is given in AMU, just replace this AMU with 931.5 and write mega electron volt. That will give you the equivalent amount of energy. Multiply and tell me.
Sir, 342.12225.
342.1225.
Yes, sir.
1225, these many mega electron volt. This is the binding energy, guys. But what is asked in the question? It is binding energy per nucleon that is asked. So let's calculate the binding energy per nucleon. So it is 342.1225. The whole divided by what? The number of the mass number, right? Mass number is 40. Can you divide it with 40 and tell me?
8.55.
8.55. Huh?
Yes, sir.
So 8.55 mega electron volt is what is the binding energy per nucleon of whom? Of a calcium stable nuclei. Right? Of a calcium stable nucleus, sorry. Now let's look at the graph. Mass number is how much? Mass number is 40, right? So let's say 40 is somewhere over here. If I take this as one line, okay, a line perpendicular to x-axis, then I'm taking a line perpendicular to y-axis such that it is meeting at this point. Is this not the value that you got actually? What is it you got? 8.55 means exactly the midpoint. Are you guys able to understand? So this is what you people found. So I understood how to find this. So like this, if you know, since this is going to be common for everything, right? What is common for everything? Mass of neutron and mass of proton, theoretically it is the same. But what is going to change? If you know the data from the mass spectrometer about the actual mass of every nucleus, you are going to use the same logic and find out. And if you plot the graph, you are going to get a shape like this. So this shape, according to the concept of binding energy, will tell which nucleus is more stable. So what is the concept of binding energy? It says that more is the value of the binding energy per nucleon, more stable the nucleus is. Right? So if you look in that concept, then the nucleus which is going to be more stable is iron actually. That is from this table. Guys, am I clear?
Yes, sir.
Yes, sir.
So since it is deleted, I'm not explaining all the story. This is the explanation of binding energy curve. I'll give you an outline. You can go through it. If you have any doubt, you can approach me. Okay. So it tells you about how the shape varies. The binding energy per nucleon increases sharply with mass number up to 20. So till mass number 20, it is going to increase sharply. So those kind of descriptions will be given. Okay. So based on this graph, it is observed. Okay. Based on this graph, one thing that is observed is the average binding energy per nucleon is about 8.5 mega electron for nuclei having mass number ranging from 40 to 120. That's what we calculated. Okay. For higher mass numbers, the curve drops slowly. That is for a mass number of how much value? 236. If you observe, the curve drops slowly. The 236 is what is for uranium, and its binding energy per nucleon is 7.6 mega electron volt. Hence, since the binding, since compared to the average binding energy of 8.5 mega electron volt, if you observe the 7.6 electron volt, since it is less, uranium is one of the most unstable nuclei. And those unstable nuclei have a phenomenon within them which is called as radioactivity, and those kind of nuclei are said to be radioactive elements. Guys, are you able to understand the connection? Okay. Now listen. The lesser amount of binding energy for lighter and heavier nucleus explains the concept of nuclear fusion and fission respectively. I am sure you would have heard these words at least. When you not know what it is, you would have definitely heard. In your 10th in the sources of energy chapter also, this is there. Right? Fusion means combination, fission means disintegration. So what will happen is a large amount of energy will be liberated if lighter nuclei are fused to form heavier one. Similarly, if the heavier nucleus gets split into lighter ones, that is during the fission process, energy is released. Right? In both the cases, the energy will be released. In the first case, what will happen? If you have a lighter nucleus, so lighter nucleus means they're talking about the nucleus somewhere over here, this column. So when you talk about the lighter nuclei, look at the energy levels they have. They have very small energy level. So they should also be unstable, no? But what kind of property will happen is, since they cannot get disintegrated means they cannot get further subdivided into smaller atoms than them. What can we do is they can get combined. So they participate in the process of nuclear fusion, whereas heavier nuclear like uranium and everything will participate in a reaction called as nuclear fission. Okay. So then comes the nuclear force. Nuclear force is a theoretical concept. You can just go through it. Okay, anyways, I'll explain it. Listen. So nucleus of an atom consists of positively charged protons and uncharged neutrons. So according to Coulomb's law, what will happen? The protons must repel each other with a very large force because they are close to each other, and hence the nucleus must be broken into pieces. But this is not happening. Why? It means that there is some other force in the nucleus which overcomes the electrostatic repulsion between the positively charged protons and binds the protons and neutrons inside the nucleus. That force is what is called as nuclear force. Okay. So there are certain properties with respect to nuclear force. If I ask you about electrostatic force is going to exist when you have charges, right? Whereas nuclear force is charge independent. It is the same for all three types of pairs. So what are all the pairs that you can find inside the nucleus? A neutron and neutron repulsion can take place. A neutron and proton can take place, and a proton and proton can have a force between them, right? So there are three pairs of nucleons: neutron, neutron, proton, proton, and neutron, proton. This shows that the nuclear force is not electrostatic in nature. Second, nuclear force is known as is the strongest known force in nature. Third, nuclear force is not a gravitational force. Nuclear force is about 10 power 40 times stronger than the gravitational force. Next, the last point is, it is a short range force. It is very strong between two nucleons which are less than 10 power minus 15 meter apart, and is almost negligible at a distance greater than this. On the other hand, electrostatic, magnetic, and gravitational forces are long range forces that can be felt easily. You cannot feel the nuclear forces because it is a short range force. Am I clear, guys?
Yes, sir.
Sir.
Yeah. So with this, technically, the chapter is over. But as I told you, I'll just give you an outline. I'm not going to get deep into it. I'll just tell what they are so that you can read it on your own. So I told you about radioactivity, right? So radioactivity is a phenomenon which happens naturally. It's a spontaneous process. Okay. So by now you should have understood what is this radioactivity. If you have a nucleus which is unstable, what do you mean by unstable? It has more atomic mass and less binding energy per nucleon. Okay. So when this kind of an unstable nucleus undergoes a spontaneous means natural emission of highly penetrating radiation such as alpha, beta, and gamma rays by heavy elements having atomic number greater than 82 is called as radioactivity. Okay. And the substances which emit these radiations are called as radioactive elements. One of the examples of that radioactive elements is uranium. I told you that, right? So here an important point to be noted is it is spontaneous and is unaffected by any external agent like temperature, pressure, electric and magnetic fields. So try to understand, an unstable nucleus will get disintegrated into smaller nucleus along with some liberation of either alpha particles, beta particles, or gamma rays. Okay. So what is an alpha particle? This is what we have seen. So alpha particle is a helium 2 plus nucleus, all those stories you know, right? So the points which you can read to understand better is, what can you say about their ionization capacity? How are they getting deflected by electric and magnetic fields? All these points you can read. Okay. Similarly, when you talk about beta rays, it can either be beta positive or beta negative. Beta negative is nothing but an electron. Beta positive is called as a positron. Positron. And there are some more properties given here. This also you can read. Similarly, properties of gamma rays also you can read. Okay. So this radioactive disintegration law and all is not needed with the current theory. So why I explained radioactivity is because radioactivity is a natural process of disintegration. Then we have a concept called as nuclear fission, right? So nuclear fission is man-made. Nuclear fission is also a kind of radioactivity, but this is created. So what you do is, if you have a stable nucleus, by creating some disturbance in the arrangement of it, you will make it unstable and then make the process generate. So that's why it is called as man-made process, where in the nuclear reactions, one of the reactions is fission and the other one is fusion. Okay, this also you guys can read. If at all they teach in your school or something like that, you can let me know. That time I'll explain. To my knowledge, it is not there in your syllabus. Okay, so that's all with this chapter. Any doubt, guys?
No, sir.
Okay. So I'll share this notes after the class. You can go through it. So as I told you, after that we can actually start semiconductors. That is the last chapter in this, in your 12th standard. Okay, by this week I'll complete it. Okay. So this is called as semiconductor electronics, which is called as material devices and simple circuits. These are all the things we are going to see. Actually speaking, this is a very big chapter, but your syllabus is actually broken down into smaller parts. So they have removed Zener diode and its characteristic as a voltage regulator and all those things. So what we are going to see is, I'll just give you an introduction, then I'll explain everything in detail. We will see what is the introduction of this chapter. We will see what is the classification of metals, conductors, semiconductor. We'll see what is intrinsic, extrinsic semiconductor. Then we will see PN junction diode, semiconductor diode, and seventh part. From here onwards, it is not there. Okay. Let's get into this chapter. Okay. So if you see the name of the chapter, it is semiconductor electronics, right? So electronics is a branch which is leading in the world today, right? We are using mobile phones, your laptops, everything. Everything inside it has a semiconductor device in it. So what exactly are these semiconductors? Why do we need to study about them? We have already learned something called as conductors. We have learned what are insulators. Now, what does a semiconductor actually mean? Okay. So let's try to answer that first. Let's see the introduction. So in reality, what happens is, it has been observed that there are certain materials like germanium and silicon which have resistivity neither very low like good conductors nor very high like insulators. They are intermediate. Okay. So if you talk about the materials like germanium and silicon which have the resistivity between that of a good conductor like copper and insulator like glass, then these kind of materials are what are called as semiconductors. Okay. So first, if you need to give a proper definition to it, you can give a definition to it in terms of its resistivity, because that is how we define conductor. If someone asks you what is a conductor, what is a good conductor, what are you going to say? Okay, I put a question like this: what is a good conductor of electricity? You are going to say the material which is going to allow the charges to pass within it is called as a good conductor, right? Insulator is the one which is going to block it. So in a similar context, when you talk about a material which has a resistivity between that of a conductor and insulator, that's what we call it as a semiconductor. So resistivity of a semiconductor lies approximately between 10 power minus 2 and 10 power 4 ohm meter at room temperature. Okay, this is the place. There is a variation. Okay. Next is the question. So here I told room temperature. What will happen if I change the temperature? It is not possible for us to maintain room temperature every time. For example, you are using your mobile phone. It is not possible for you to have your mobile phone every time outside. Right? You might be sitting in some air conditioner, or you might be in the ground sometime. When you see it, it gets heated up, right? So all these things are happening. Inside, what is going to happen to the semiconductor device that is present on the motherboard? Right? That's what we need to understand. So the resistance of a semiconductor decreases with increase in temperature. Okay, and that will also happen only over a particular temperature range. So let's try to understand the concept of temperature coefficient. So for a conductor, if I say something like this, R is equal to R naught into 1 plus alpha delta T. We have already seen this, right? So resistance of a conductor varies with temperature according to the equation R naught into 1 plus alpha delta T, where alpha is called as what? It's called as the temperature coefficient of resistance, right? So generally, if the value of alpha is positive, listen to it carefully. If I say alpha is positive, that is if it is greater than 0, then it means, okay, so when the value of alpha is greater than 0, it means that resistance will increase with the increase in temperature. Whereas if I say alpha is less than 0, then resistance will decrease with increase in temperature. That is, if you try to increase the temperature of a semiconductor device, it is observed that its resistance is going to decrease. So one important parameter with respect to temperature coefficient of resistance is, for a semiconductor, there is a negative temperature coefficient. Okay. So this behavior is contrary to that of the metallic conductor, for which the resistance increases with increase in temperature. So the elements which are classified as semiconductors are silicon, germanium. So generally, germanium and silicon are the most widely used semiconductors. Am I clear till this point, guys?
Yes, sir.
Now, we will be discussing about the energy concept. So till now, we differentiated semiconductors between a conductor and insulator based on its resistivity. Now, if I have to speak in terms of the energies possessed by the electrons in their valence band, okay, in the valence shell, that is called as the energy in the valence band, we will see how conductors, insulators, and semiconductors are classified on the basis of the band theory, energy band theory. Okay, so this is called as energy band theory. Understand, guys? So there are three bands that we can always find. One is called as valence band, one is called conduction band, and the third is called as the forbidden energy gap. So there are two bands and a gap existing between them. Okay. Even before we look into the main context, let's try to understand what this valence band is. Right. So what do you think this valence band is? Now listen. So since we are talking about semiconductors, we need to look into the conductivity of that material, right? So whether it is a
Sir,
semiconductor, conductor, yeah, tell me.
is it concerned with the valency of the material?
You can say something like that. Yes. So we know one concept, right, from the atoms concept, atoms chapter, that electron in a particular orbit will have an energy associated with it. So when the electrons are moving, they have certain energy associated with it. So what will happen is, if you take every electron, they will not exactly have the same value. They might have range of values which can be put under a small box like this, which we call it as valence band. Let's first understand why we need to study about it. What you told is partially right. Okay, let's try to answer this question, guys. So I'm thinking like this. So whenever I have a semiconductor, let's say I've given you a semiconductor, what are you going to check for it? You need to study the properties of conductivity of that material. Right? When I say conductivity, when can a material become a conductor? That's the question. Only when it has, can I say when it has free charges? Right? So that is when the conduction is going to take place. Now let's try to understand. Even we studied this in photoelectric effect also. So there is something called as photoelectric current, but we didn't connect any potential source. But we are able to find some photoelectric current. That is, you are able to generate free electrons. Even without connecting the atom across a potential source, you are able to generate photoelectrons, right? How did we do that? When you have electrons in the valence shell, there will be certain materials in which the valence electrons are loosely bound to the nucleus. So when you supply some amount of energy which is sufficient enough for it to escape out of the valence shell by overcoming what? The electrostatic attraction between the electron and the nucleus, then what will happen? This electron will become a free electron and it will have the tendency to conduct because that is acting as the charge carrier, right? So when this kind of a phenomenon is able to happen, we can technically say, according to the energy band diagram, we can say that the electron which is present in this particular bracket has actually jumped into a bracket of conduction. Means it has developed the property to conduct. Are you able to understand? So the amount of energy that you need to supply so that the electrons in the valence shell is able to jump into electron in the valence band is able to jump into the conduction band is what is called as forbidden energy gap. So the energy level which is measured for forbidden energy gap is generally in terms of electron volt, and this kind of a diagram is what is called as energy band diagram. Let me read out the points for you so that you will understand. Concentrate, guys. So when you talk about the atoms of a solid, they are arranged in a regular repeated geometric pattern. This you would have learned in your solid state chemistry. BCC, FCC, all these things are there, right? So when you take a solid, in a solid, there is a regular geometric pattern that is being followed, and the electrons in the atoms revolve around the nucleus in certain permitted energy levels. This also we know according to Bohr's theory. So what about the electrons in the inner shell? They are strongly bound to the nucleus, so no question about them for conduction. So band which is occupied by the valence electrons or a band having the highest energy is defined as valence band. The valence band, what can happen? In the valence band, it is not necessary that it is going to be completely filled, right? The valence band may be partially or completely filled. This band can never be empty because there should be some valence electron. Some outermost orbit should definitely exist for an atom, right? In some materials, the valence electrons are loosely bound to nucleus, like how it happens in the case of metals. So even at room temperature, what will happen is some of the valence electrons can leave the valence band, and those electrons are called as free electrons. That's what I told you. Okay, and these free electrons are the ones which are responsible for what? Conduction of current in the conductor, and henceforth known as conduction electrons. So the band occupied by these conduction electrons is what is called as conduction band. Okay, this band may be an empty band or partially filled band. Why we are calling it as empty band is because in the case of insulators, it is not possible. It might be impossible for you to push the valence electrons into conduction band because they do not show the property of conduction at all. Right? That is why it can either be empty or it can be partially filled. So the separation that is existing between the valence band and the conduction band is known as forbidden energy gap. To put it in other terms, it is the amount of energy we need to supply to whom? To the electrons in the valence band to jump into the conduction band. Okay, so that's what is written here. If an electron is to be transferred from valence band to a conduction band, external energy is required, which is equal to the forbidden energy gap. Guys, am I clear? So this is just an introduction of the energy band diagram. So don't forget, this is what is called as energy band diagram. If you have to speak in terms of exam point, in exam point, they will ask you about the difference between conductors, insulators, and semiconductors using the energy band diagram. Right? Are you guys able to understand this? Okay. So the next concept is insulators, semiconductors, and conductors based on the energy band diagram. Even before we get into the context, let's use some logic and tell the answer. If I put a question like this, the forbidden energy gap. Okay, the forbidden energy gap for insulator, conductor, and semiconductor. I am asking a question like this: will it be high, low? I'll put it like this: very high, high, low, medium, nothing. So for insulator, it is going to be
Very high.
very high, or it can
Very
be high
high.
also, depending on what kind of an insulator you're dealing with. When you talk about a conductor, it will be the least. To put it in other terms, there will actually be no energy gap at all. It is nothing. Means the conduction band and valence band will be so close to each other that they will be almost overlapping on each other. Whereas for a semiconductor, it will be medium. Okay. So that's what I'm going to explain using this. So if the energy gap between the valence band and the conduction band is approximately 5 electron volt, then that kind of a material is classified as an insulator. Okay, all these things I'm talking about the room temperature is. Okay, as I've told you the whole story, this part alone you can read. It is easily understandable. Okay. Similarly, when you talk about a semiconductor, it has a narrow band gap, which is approximately 1 electron volt. I'll come to this. Whereas when you talk about conductors, they are like almost overlapping on each other. Okay. Now, since our interest of study is about semiconductors, what exactly is going to be the value? I told you there are two important semiconductors that are used. One is germanium and the second is silicon. So when you talk about the forbidden energy gap, it is generally of the order of 0.7 electron volt for germanium and approximately 1.1 electron volt for silicon. Okay. Are you guys able to understand? So this value alone is to be remembered. Every other story you can read. Okay. Now listen. So this will be the last topic of discussion for today. Concentrate. I'm just going to introduce two terms that are used in semiconductors. When you talk about conductors, okay, in a conductor, if I ask you what are the majority charge carriers, what will you say? Majority charge carriers means who are actually responsible for the conduction within a material called conductor or within a conductor. It is
Electrons.
electrons, right? So in semiconductors, apart from electrons, so there, let's try to just connect the dots. I'm going to explain this. So when you take a conductor, if I connect positive source here, negative source here, electrons are there, the electrons are going to move in this direction, and the conventional direction of current is taken in the rightward direction. So can I say the direction of current is the direction in which a positive charge would flow? Means, am I trying to say that protons are actually flowing? It is assumed that if the positive charge was there, then it would have flown from higher to lower potential. That is taken to be the conventional direction of current. So there we don't have anything like positive charges which are present inside the material of a conductor. Whereas when you talk about a semiconductor, you have electrons and you have something called as holes in the conductor. Now try to understand this. So I told you germanium is one of the semiconductors like silicon. So if you take from the periodic table and write its and split and write the number of electrons and electrons in each orbit, it is observed that it has 4 valence electrons. Okay, so it has 4 valence electrons. So wherever the valency is 4, what kind of a bond is it going to form?
Covalent.
It is going to form the covalent bond, means the sharing of electrons is going to take place. So when this covalent bond is formed, one germanium atom is going to get combined with another germanium atom like this, right? So it will try to complete the octet structure. So it will try to have 8 electrons around it to attain the stability. Okay. So I'm talking about the germanium from a conductor called as pure semiconductor. The other name for pure semiconductor is intrinsic semiconductor. Remember this word, okay? What it is, I'll explain it the next. See, there is nothing to explain in this. Intrinsic means pure form. Like if you take germanium, let's say you're trying to get that material from somewhere. If you buy it in the purest form, that's called as an intrinsic semiconductor. So that's what is given here. The electrons in intrinsic semiconductor. So In intrinsic semiconductor, that is in the purest form, what will happen is the electrons, when they are bound together, when this particular germanium atom is subtended to high temperature. Okay. So when it is subtended to high temperature, then what will happen is the electrons which are present in the purest form of semiconductor will jump into the conduction band. Okay. So this is what will happen at room temperature. So A will happen at room temperature and B will happen at higher temperature. So how many valence electrons? 1, 2, 3, 4, 5, 6 valence electrons are there. Out of the 6 valence electrons, you are able to see, due to the temperature being supplied, there are 3 electrons that have jumped into the conduction band. Now it has developed the property of conduction. But the question that comes is, when the electrons have actually jumped into the conduction band, they leave back a vacancy, right? So out of the 6 electrons which were present, now we have only 3 electrons. So there are 3 vacant places that are there. So those 3 vacant places which are created by the electrons in the valence shell by jumping into the conduction band are what are called as holes. So hole doesn't mean literally a hole, the vacancy of electron, right? If an electron at a particular location is missing, then that particular location is said to have a hole. It is assumed to be a virtual positive charge. Okay, that is happening because what has happened initially, it had 8 electrons. See, you are able to see these 8 electrons 1, 2, 3, 4, 5, 6, 7, 8. It has 8 electrons. In a similar way, here also you have 8 electrons. But by supplying the temperature, what has happened is the electron which actually participated in the covalent bonding has escaped. Now, what has happened? This has become a free electron. When I say free electron, virtually you have to remember that it has jumped into the conduction band. So, what is left out in the bonding structure? The hole is left out. Now, this material, due to this free electron, will develop the property of conduction. Okay. Are you guys able to understand? So in the valence band, I'll read this out, listen. In the valence band, a vacancy is created at a place where the electron was present before it had moved into the conduction band. This vacancy is called as hole. So consider a pure germanium crystal, which is nothing but intrinsic form. It has 4 electrons in its outermost valence bond orbit. These electrons are known as valence electrons. When 2 atoms of germanium are brought close to each other, a covalent bond is formed between the atoms. So, if some additional energy is received, one of the electrons contributing to the covalent bond breaks and it's free to move on the crystal lattice. While coming out of the bond, a hole is said to be created in its place, which is usually represented by an open hole. You put a circle like this, that's a hole. So, what will happen is, listen. So, logically, what will happen when there is a hole? It has the tendency to attract the electrons from the neighboring atoms. So what will happen is, if the electron in the neighboring atom has jumped from here to neutralize this hole, then can I say that a hole is created here? Try to understand, guys. So the electron from the neighboring atom, if it jumps into the hole, okay, if it jumps into the hole to neutralize it, then from whichever location the electron has jumped to neutralize it, at that particular location a hole is created. Similarly, to cover this hole, an electron from the neighboring atom will again come. So, due to which what is happening is, you are able to see the movement of holes that are taking place. Am I right? So, actually, what is happening? The hole is moving, but hole, what did I say? It's a virtual positive charge. The hole is appearing to move due to the motion of whom?
Electrons.
So, due to the motion of electrons. Okay. So this point should be in your mind. Actually, the moving particles are electrons, but since the hole appears to move like this type of a current is called as hole current. We call it as hole current. Some books use this name. At that point, you should not wonder what it is. It is actually the electron jumping from the neighboring atom to make the hole move. So that's what the point is. So an electron from the neighboring atom can break the covalent bond and can occupy this hole, creating a hole at another place. Since the electron has unit negative charge, the hole is associated with unit positive charge, but it doesn't mean it's a proton. Okay. The importance of hole is that it may serve as a carrier of electricity in the same manner as that of free electron, but in opposite direction. Okay, because the electron is the one. If the electron is flowing from right to left, hole will move from left to right. That's what happened. Am I clear, guys? So this is the basic introduction about the concept of electrons and holes in semiconductors. Okay. Next class, maximum 45 minutes, we can complete this chapter. So till whatever we have discussed, is there any doubt that you have?
No, sir.
Okay, then. Just wait for a minute. Don't log off.
No, sir.